Hello everyone, in this video we will be talking about the Dijkstra's algorithm. Why we need this to solve the single source shortest path problem. So we will be having the single source through which I want all the shortest path of all the other destination. For example, this is my source vertex. Now I need to find the shortest path of all the other vertices from these six. So the shortest path between 6 and 4, shortest path between 6 and 5, and so on. So I need the shortest path from 6 to all the other vertices. So to cater such kind of problem, I have this algorithm. Now how it works, let's understand this through an example. So this is the graph and this is the directed graph. So let's consider A as my source destination, and at the end of this example, what I have to find? I have to find the minimum distance of all the other vertices from the A. Okay, so what we will be doing basically in this question or in this algorithm, we will be maintaining the table through which I will be finding the minimum distance of all the vertices from A. Initially, okay, so the values which I will be writing in the table is the distance from A to the vertices written here. So initially, what is the distance between A and A? That's 0. What is the distance between A and B? That's infinity. Because initially I don't know the distance between them, so I took the maximum value possible. So distance between A and C, A and D, and A and E initially taken as infinity. Now the second step, we will be finding the directly connected vertices from the visited vertex. So in this case, my visited vertex is A, directly connected vertices is B and C. So now I will be writing the distance between them from A. So the distance between A and B is 10, distance between A and C is 3, and the end is gonna be infinity from carrying from the above row. Now what I will be doing, I will be searching for the shortest distance, that's 3. So now what vertex I will be visiting, that's C after A. So understand this through an animation. So C, from A, I have visited C, and similarly, I'm maintaining the set where I will be first visiting my source vertex and then C. Why? Because it's the shortest possible vertex from the A. Okay, now let's continue this approach. Okay, so now from my visited vertex, what are the directly connected vertices? B, D, E, all are connected to C. So let's write their distance from A. Make sure in the table, whatever values we are writing the distance of this vertex from A. Okay, so let's understand this. So why 7? Okay, so why 7 we are getting? Because we want to write the distance between A and B, but through C. Okay, because that's the vertex I have selected. So A to C, the distance was 3, and C to B, the distance is 4. So the total distance will be 3 plus 4, that's why this is 7. Similarly, the distance between C and D is 8, and the distance between A and C is 3. So 8 plus 3 is 11, and 3 plus 2 is 5. Again, I will be selecting the shortest distance in this third row, that's 5. Which vertex it is? That's E. So the third vertex which I will be visiting is E. So that's why this is pink in color now. And this is appended in the set S as well. Let's move forward. Now again from this visited vertex, I will be selecting the directly connected vertex. That's D in this case. So the value of B will be copied from the above row. So that's going to be 7, 7. But why D is again 11? But the value of E from A is 5, and 5 plus 9 gives me 14. But then why I have written 11 and not 14? Because we are finding the optimal solution. So which is shorter distance, 11 or 14? Of course 11. Since my table already have a better solution, I won't be eliminating or changing it. So however, the distance between A and D through AC is 14, but I will be writing 11 only. Why? Because I have a better solution there. Instead of going A, then C, then E, and then D, which is 14 units of a distance, how I will be going from A to D, that's through A to C to D. That's only 11 unit distance. Okay, so I have a better solution already. Therefore, I'm not changing the value of D in my fourth row. Again, I will be selecting the minimum distance, that's 7. So the B vertex I will be visiting first. So B pink and also appended in this S set. And the last vertex is D, so of course G will be appended. Okay. Okay, D is appended. But why 9 we are getting? Let's understand that. So the last vertex which I got was B. So A to B, how many distances I need to have? That's 7. And from B to D, how many distance was there? 2. So 7 plus 2 was 9. So already in the above row, it was visible that A to D, I already have a path which I need to travel 11 units. But from A to B to D, I need to only travel 9 units. So of course, it's a better solution there. So I will be changing 11 to 9. So I hope now you understand why I took infinity in the starting. So that's obviously going to change, okay? Because this is the biggest one and we want the smallest one. So that's all the idea of this algorithm. Now let's summarize it and let's understand the pseudocode. That's very important. So Dijkstra algorithm is a solution to a single source shortest path problem. It works both on directed and undirected graph. However, there's a drawback or a disadvantage of the Dijkstra's algorithm that the edges should not have a negative weight. If it has a negative weight, this algorithm fails. Now, what kind of approach we are taking? We are taking a greedy approach. What greedy approach says, for example, I have a problem. I will be dividing the problems into the sub-problems. And I will be finding the best optimal solution for each subproblem so that together I get the best solution for my original problem. I hope you got the point. So this is a greedy approach. So basically I'm selecting the vertices that has the minimum distance, and through that vertex I'm traveling to the other vertices. So I'm dividing my total problem into the subproblems and finding the best solution for each subproblem. Now for this algorithm to work, what inputs I want? Obviously I need to have the weights of the edges and the vertices. And what output I will be getting? I will be getting the shortest paths for each vertices through a source vertex. Okay, now finally let's understand the pseudocode. So the first 3 steps actually shows the initialization. S is my initial or the source vertex, and the distance from the source to source is 0, and the distance of all the vertices except my source vertex is taken as infinity initially. Obviously I'm maintaining the set S where I will be appending the vertices I'm visiting. Initially it's gonna be 5, and then I have a set Q where I have all the vertices. Okay, Q should have some vertices. It can't be empty. Therefore, we won't have any graph. Okay, so this was all the basic things. Now let's talk about the main logic of this algorithm. So what is this U? So U is the minimum distance of any vertex from my source vertex. So let's say that I have a vertex A, and the distance I have a vertex this B. Let's select this C. Let's select this C. So the minimum distance between my source vertex and the C is 4. Okay. So I will be appending it because this is the minimum distance I'm getting right now. So I will be appending the C into my S. So this is my S. So S will have my source vertex, that's A. Then I will get C because that's minimum. Let's consider this 5. So B and C, which is minimum, C will be the minimum. Okay. So this is, I have appended U into the set S. Now what I will be doing, I will be finding the neighbors of my U. that u is the appended or the appended vertex. Okay, so now I will be finding the neighbors of the u. In this particular case, what is the neighbor of c? That's d. Okay, now what I will be finding that the distance between a and d directly is, for example, 12, and the distance between a and d through c is, for example, 7. So this is gonna be 12, and distance between u was 4, and the weight between u and v was, in this case I have taken as 3. So the total distance is 7. So the distance of v directly is greater than the distance between the source and v using u. Then of course we don't want the greater distance. So what we will be doing, we will be changing the distance to this. So we are actually setting the new value for the shortest path. Okay, so this is how we will be returning the distance. That's all about the Dijkstra's algorithm. The last point which I need to discuss is the drawback or the failure of the Dijkstra. Basically, this doesn't work for the negative weights as discussed before, but let's understand the logic. So for example, this is my source vertex. Okay, now from source vertex, let's find the distance, minimum distance from 1 to 2. So if I'm going directly here, so what will be the distance? That's 3. But if I'm going through this particular path, what will be the distance? 5 plus 2, that's 7. 7 plus minus 10, that's minus 3. But according to the Dijkstra, what I will get? 3. But what is a better optimal solution I have through this graph? That's minus 3, because minus 3 is smaller than 3. And I need the shortest one. Okay. If you people have a confusion that how we can get a negative weights, so please remember that the distance is just an example. These edge weights can be anything. It can be energy, like a thermal plant, where many processes are connected to each other, and some are consuming the energy and some are releasing the energy. So of course, edges can have the negative weights. So I hope you understood the failure of this algorithm, the pseudocode of this algorithm, working, and why this is needed. So that's all in this video. Thank you so much for watching.